Let's look at one special 1D motion with a constant acceleration. And this one is called the free fall. So let's say you have an object and you let go of this object and then you will fall down to this position here. So in order to study this kind of motion, the first step is to set up a coordinate system. So in this case, I draw the y-axis pointing upward as the positive direction. And using this coordinate system, we call this initial position y0 for the object. And the final position here, we call it y. So now let's write down the condition here. So since we have a constant acceleration pointing downward, right, due to gravity, and that acceleration is in the opposite direction to the y-axis. So that's why when I write down ay here for the acceleration for this 1D motion, I need to write down a negative sign. I need to write down negative g here. Right? G is the gravitational acceleration on the Earth's surface. Okay, so let's write down this ay equals negative g here as the starting equation, right, to solve for either the position or the velocity of the objects as a function of time. And again, this initial position corresponds to time interval t0. And this one, the final position here, corresponds to the time, right? A time variable t. And starting from here, we remember that the kinematics formula for the velocity, so final velocity here, right, is a function of Vy0. So that's Vy0 is the initial condition here. Initial velocity of the objects Vy0, okay, plus ay times t minus t0. That's the expression for the final velocity Vy. And since ay equals negative g, so we get Vy0 minus g t minus t0. Okay, so that gives us the expression to calculate the velocity at any instant t. Okay, so of course, in the special case when t0 is 0 seconds, so let's say you start the counting time at 0 second for this t0, then this expression reduced to Vy equals Vy0 plus ay times t or minus gt. Okay. All right. So that's again a special case when we consider t0 equals 0 second. So now let's write down further for the position vector. So y, if we solve this constant acceleration problem, then y equals y0 plus Vy0 t minus t0 plus 1/2 ay t minus t0 squared. Okay, so again, let's substitute in ay's expression, so we get y0 plus Vy0 t minus t0 minus 1/2 g t minus t0 squared. So that's the expression for position y as a function of time. So it depends on two terms. One is the initial velocity that gives us this linear dependence of t, and the acceleration gives us this second order for this t dependence. And I also want to mention that the y-axis here, right, in this coordinate system is actually arbitrary, so you can also pick your y direction to be pointing downward. Okay, so now in the second part, let's look at this second choice here. So let's say I want to pick y. Axis pointing downward. Now let's write down this condition now. So the objects fall down in this direction. You still have this y naught and y here at time t naught and t, where you have vy naught and vy. But now the acceleration is still pointing downward. However, we need to write down ay equals positive g, because the direction of ay is now in the same direction as the positive y's direction. So it's positive g. Okay, so let's write down ay equals g here. So if you solve this velocity and also the position, then you're going to get the following. So vy becomes vy naught plus g t minus t naught, and y here equals y naught plus vy naught t minus t naught, and plus 1/2 g t minus t naught squared. Okay, so this expression may seem not so obviously different from the previous one. But let's look at one numerical substitution here. So let's say we know that the vy naught equals, let's say vy naught has a downward velocity and is, in this case, because y-axis is pointing upwards, so let's say it has 1 meter per second value here, and because direction is downward, so we get a negative sign here. Okay, and ay now becomes negative 9.8 meter per square second. And let's also pick, let's say, ay here to be, let's say, 10 meter. Let's say 10 meter above the origin here. So y naught equals 10 meter, but now it's positive because it's above the origin. So if I substitute in this expression, I will get 10 meter positive, and vy naught is negative, so minus 1. And also let's take t naught equals 0 seconds, so we get 1 meter per second times t here. And here we get negative 1/2 times 9.8 times t squared. Okay, so let's look at the same numbers, but looking at this y coordinate pointing downward. And in this case, vy naught is going to be positive 1 meter per second, and ay here is also positive 9.8 meter per second. We still think about y naught equals, let's say, 10. Oh, so now let's say the origin is here. O here is above the floor, then above the ground level, and we also have, let's say, y initial is. So now y initial is a tricky one. So it's going to be it will depend on the distance to this origin here, and let's say origin here is above ground level by 10 meter. 10 meter above the ground level, then y naught is going to be 0. Right, initially we set, in the previous case, we set the ground level at the origin here. So that's ground level. So now the ground level is here, the 10 meter, and origin is 10 meter above the ground level, so we get y naught equals 0 here. Okay, so again, you have freedom of choosing the direction of the y-axis and also the origin of the y-axis. Okay, so now let's write down here. So we have 0 here. We want to know that now it's plus sign times t, and g here is also plus sign, so 1/2 times 9.8 times t squared. Okay. However, the final result would be the same in the sense of the same position here, although it's measured in two different coordinate systems, but their positions are actually the same, although their numbers appear to be different.